Hi, everyone, and welcome to session 6 of the massive open online course for the University of Nicosia's master's degree in digital currencies. This is our 10th iteration of the MOOC, and today is class 6. I'm Andreas Antonopoulos. I'll be answering your questions. We had a slight change in schedule. Perhaps some of you didn't see it or hear about it, but still 20 or so of you showed up, so that's great. Let's get started. Hi, everyone. I'm seeing you on the chat room. Can you hear me okay? Let me know in the chat room if you can hear me all right. Good sound, good video. Let's get started. Today's session is about alternative uses of the blockchain. This is not one of my favorite topics because I find that a lot of the alternative uses of a blockchain are very thin for the time being. People often ask me, what is the killer app? Is there a killer app? When will we have a killer app? And quite honestly, in my opinion, money is the killer app and will probably remain the most important application. A neutral, borderless international currency is a killer app. It's more of a killer app than most of the other things I've seen. Now, that doesn't mean there won't be alternative use of the blockchain. It just means that it might take some time before those are sufficiently developed. And in fact, many of them depend on the security and stability of an underlying currency. So maybe we have to get much further into money as a killer app before we can do many of the other things on this internet of money. First question's about smart contracts. Ali asks, how are operations conducted without having middlemen, and who does them? Can you please give us some real world examples, and which application is best for it? So, Ali, when a smart contract is executed, it is a software program. And every single participant in the smart contracts platform, let's take, for example, Ethereum, just because I know Ethereum a bit better than some of the other smart contract platforms, but the same kind of logic applies to all of them. Every single smart contract execution starts with a transaction. So someone makes a transaction, and that transaction has a contract as its recipient and tells that contract to do something. Basically, it's the input to a program. Smart contracts are just software after all. So what happens then? Who runs the smart contract? Well, the simple answer is everyone runs the smart contract. Everyone takes everyone who's participating in the Ethereum network, everyone who's running an Ethereum node, everyone who's running a business that's running an Ethereum node. The nodes themselves, the Ethereum nodes, the clients, the computers that are running as part of the Ethereum network, will receive that transaction. In order to validate that transaction, they execute the smart contract and they pass as input to the smart contract that transaction inside what is known as a virtual machine. And a virtual machine is basically a simulated computer. So in Ethereum, that's the Ethereum virtual machine, or EVM. And that simulated computer takes the transaction that was the input to the smart contract. It takes the transaction contract code, the contract code that is recorded on the blockchain, and it runs that as a software program with that input. Now, if all goes well, and that transaction should run successfully and produce some change in the state of the system, meaning that a variable is updated, maybe a payment is sent, maybe some money is deposited, maybe something changes ownership, maybe, again, part of the memory or data store of the contract itself is updated with new values. These state changes are then recorded on the blockchain. Now, if you imagine thousands of computers all running the same software, they're not running it at the same time. There might be some slight differences in time. They're each running it locally on their own machine, and they're each using as input the same transaction, the same blockchain. Now, given all of that, they should all arrive at the same conclusion. They should all run the program identically and produce the exact same results. Those results are what's recorded on the blockchain, those state transitions. So all the blockchain in a smart contract platform We record the transaction as well as all of the results of the transaction, which may include events and changes to the state of the blockchain. Everybody can validate that they got the same result as everybody else. And when they download a new confirmed block from the Ethereum network, they can validate that block by running all of the transactions and smart contracts and seeing if they agree with the results that the miner has included in there. If they don't agree, then they will consider that block invalid and reject it. So therefore, just like in other blockchains, like in Bitcoin, everybody validates. Everybody who is participating as a node on the network validates every transaction. And in the case of Ethereum, to validate a transaction, that may mean, in most cases, means running the smart contracts and arriving at the same results as anybody else. There are no middlemen that are running this. This is done in a decentralized way. Now, all of that refers to the execution of a smart contract that uses information from within the blockchain. Now, when it's running in the EVM, it has a very limited set of information it can act on. And that's because all of that information has to be part of the consensus rules. It has to be the same for everybody who's trying to run that contract so that they can all validate it the same. That means that smart contracts are very limited in how much information they can access, meaning that they can't access information about the real world. They can't say, what is the temperature today in Pensacola? That's not on the Ethereum blockchain. They can't say, what is the price of Ether today? Or something like that. And so as a result, there are external services that sometimes supplement smart contracts, and these are called oracles, which leads us straight into the next question by DDA. How can we make sure that an oracle feeding information to a smart contract is not corrupt? That's a great question, Didier. In fact, that's the biggest challenge with the technology of oracles. So you have this compromise situation whereby smart contracts can only act authoritatively and within the consensus rules on the information that's already stored in the Ethereum blockchain and the transaction they just received. And they can't validate the truth of anything that's in the transaction. They can't validate what's happening in the real world. For that, we sometimes use external services called oracles. But the problem with that is if you trust that oracle has enormous power. Let's say, for example, that you had an insurance company, and that insurance company has a clause that says, if it rains more than 30 inches in this particular region, that will trigger a claim on an insurance over property, so to cover rain damage. And so that smart contract in there has to constantly check how many inches of rain have fallen in a specific area. Now, you can use an oracle for that. You can use an oracle that publishes every minute or every hour the cumulative amount of rain for the past 24 hours. And that if it exceeds a certain threshold, then you could trigger an insurance payout. Here's the problem. Now you've centralized a lot of the control and power into this oracle. So where's this oracle running? In most cases, this oracle is running outside of the Ethereum network. Or if part of it is running inside as a smart contract, certainly the information about how much rain fell in the last 24 hours is coming from outside. And that source has to be trusted. There's a couple of ways to get around this problem. One of the ways is to use a certain type of oracle where instead of asking one source for the data, like how much it rained in a specific area, you have a decentralized mechanism whereby the oracle collects information from thousands of sources and they must all agree. Effectively, you're running consensus rules on perhaps an external blockchain, a sidechain, or another blockchain that is used in order to arrive at a common truth. So at that point, if everybody out of 1,000 people who are running rain sensors in Pensacola, Florida, and they all report within the range of 28 to 30 inches of rain, then you can say, okay, that information is more decentralized and we can trust it. Why does this matter? Well, part of the reason it matters is because smart contracts execute automatically. And when they execute automatically, they also execute in a way that cannot be reversed. So imagine a situation whereby you have an insurance contract and it's going to pay out. If you hack the oracle and make it report the wrong amount of rain, exaggerating the amount of rain, and you trigger the insurance company to pay out all of these claims, then you can effectively defraud the insurance company. And therefore, smart contracts only operate on whatever information they have. If you put garbage in, you get garbage out. And one of the challenges with interacting with the real world is how do you know that information is correct? And how much trust are you putting into a single provider? If you centralize trust, then that creates an enormous incentive for people to basically compromise that centralized system because they could receive billions of dollars, presumably, in insurance payouts. Arguably, no one's going to do that anytime soon. No one is going to write a smart contract that will automatically pay out billions in the case of an event coming from an oracle. And this is where the real world of smart contracts really where the rubber hits the road, if you like, because it's exactly these challenges that mean that we're very, very far away from many of the alternative uses of the blockchain that people discuss today. Simply because you can't put that much dependence on a fully automated system, especially if it has a centralized part of trust. Gabriel asks, are smart contracts agreed upon, or are they more of a saying, this is how I function. If you want to interact with me, you have to follow these rules? Gabriel, I think part of the challenge here is the word smart contract. And for many people, this is very confusing. The word smart contracts themselves leads people to believe that this is somehow a contract as in the undersigned, I, Andreas Antonopoulos, agree upon presentation of a receipt for the delivery of oranges to pay $3 to Gabriel Gomez, et cetera, and that they have some kind of contractual element to them. They're called smart contracts, but effectively, they're not smart and they're not contracts. I like to remind people that smart contracts are really dumb programs. They're programs. They're programs that have things like, if the input is 3 and the date is X, then do Y. And these little programs are not particularly smart. In fact, they're not smart at all. They will follow the rules exactly as written in the software. And if you don't account for all possible inputs that might enter your smart contract, you can have bugs, you can have problems, you can have unanticipated situations. You can also not account for anything that's happening in the real world. Again, we talked about the Oracle problem. So, for example, in the past, people had suggested that you could have smart contracts that control the renting out of an apartment and automatically collect payment and manage insurance so you can rent an apartment in the form of, say, Airbnb, which is a known company for private apartment rentals. And the question I always ask in those cases is, okay, and how do you account in the smart contract for the fact that the next morning the guests found someone drowned in the pool, floating face down? Life has exceptions, and you're not going to write in the smart contract what happens with the insurance payment if someone drowns in the pool, or whatever else. Or if someone trashes the house, or if they set fire to it, or whatever else might happen in the real world. And of course, once you have smart contracts like that are successful, these problems tend to arise. So, Gabriel, to answer your question, smart contracts are not agreed upon. Really, they're software programs. Someone wrote that. In many cases, for different types of applications that you might want to engage in on the Ethereum network, there's more than one option. For example, if you wanted to build a token and you want to make it compatible with ERC20, or you wanted to do a crowd sale, there are 25 different implementations of that. The only part where you can say you kind of agreed is when you decide to choose to use one of those 20 implementations, you are effectively agreeing to the rules that are written in that contract. Essentially, you're agreeing to that software, and you'd better understand how it's going to execute. The truth is that most people don't really know how that contract is going to execute, and they haven't read the code. And even if they had read the code, very few people really understand all of the possibilities that can arise in software and all of the potential vulnerabilities. A perfect example of that is the DAO. A lot of people invested money in the DAO. They thought they knew what the DAO could and couldn't do, and a tiny, tiny tiny minority of the people who put money into it actually read the code. And even those people who read the code didn't understand the very, very subtle reentrancy bug that existed that led to a loss. So again, you don't agree to a contract. You run the software, you choose which software to run, and hopefully you understand how that software is going to work. But in reality, you depend on other people having run that software for large amounts of money for long periods of time. In the end, most of the security and understanding of what the contract will do comes from maturity. It comes from having this run thousands of times for long periods of time with lots of money at stake, have people try to attack it and fail, and if it's still stable and it still does exactly what you think it will do, then you can put a bit more trust into this software. Sure, it's going to follow the consensus rules. Sure, the software is going to run as written, but it's very difficult to actually know what as written means. Great. Let me check into the chat room, see how things are going, and then we'll switch to our next subject, which is sidechains. Crypto17 asks, what is your opinion of humanly readable, legally binding smart contracts? Um, well, there's a really big problem with reconciling how we do law in the real world versus what a smart contract does in code. English, and as such, any other human language, is ambiguous. It's vague. It's very, very difficult it's impossible, in fact, to write something in English that has only one interpretation. The entire basis of law is about interpretation. And over time, legal contracts have matured over particular tests so that everybody knows why there's a comma before the and in that particular clause, probably because there is a long legal case where someone got sued over the exact meaning of that Oxford comma. For example, every single word you see in an English legal contract that has a basis in English common law usually has a meaning that is very well established. The question of what the word person means, the question of what the word sale means, the question of what the word value means. These words have been tested by centuries of legal wrangling. The reason we want smart contracts to operate in code, in a smart contract language, such as Solidity or Viper or any of the other smart contracts languages, is because that kind of programming language can be made to be much, much more precise and much less ambiguous than English. So that's the advantage of smart contracts. Making them human readable is a problem because if humans are able to read them, they may assume that what they're reading means something in English or whichever other language, but what the code actually does is something else. And reconciling those two, what you think it's going to do with what it's actually going to do, is a hellishly difficult problem. Also, whether a smart contract is legally binding, making a contract legally binding or making a software program legally binding isn't really that interesting, important, or difficult. You can write a paper contract that connects to the code contract that you've put in a blockchain and bind yourself with another person to that. But the bottom line is that in all of these cases, if there's a discrepancy between what the code did and what you think you signed up for, you're going to take someone to court. And when you take someone to court, even if the payment has already been made and it's irreversible on an immutable blockchain, the judge can reverse it. And if they can't seize the ether from you because you're an awesome cypherpunk who's hidden it so well, they'll take everything else you own and throw you in a cage, and continue to take everything else. Continue to take everything else you ever earn. So, unless smart contracts are executed between entirely anonymous people who have perfect OPSEC, manage to never reveal their identity and interact entirely in virtual items without any access to the real world, there will always be interference from the law because people live within jurisdictions. And this is one of the challenges. Yes, and Justin makes a great point, which is person, sale, value are ambiguous and have still been legally challenged, and they're still challenged today. And they will never be completely unambiguous. We have thousands and thousands and thousands of cases that tell us what can and cannot be considered a person, and many of those have enough precedent behind them to have weight, but we're changing society at the same time. So does a self-driving car count as a person in the driving code? Does Alexa, if she places an order for you online, count as a person in commercial law? We don't know yet. And these things are going to lead to more challenges and more definitions about exactly what that means and when you can use those terms. So yes, the ambiguity that exists in human language and the interpretation that exists in law, these are not bugs. These are the features of the legal system. That's how the legal system works. All right, sidechains. Frank asks, do sidechains inherit any of the security properties of the main blockchain they are connected to, or are they completely independent? If not, how can we trust them? That's a great question, Frank. It depends on the implementation of the sidechain, but in many cases, a sidechain is simply another blockchain that has a way to transfer value from another blockchain. So you have two blockchains that are operating in parallel, side by side, and you can't really say one is a sidechain of the other any more than the other is a sidechain of the first. They're both sidechains to each other. But they're both independent blockchains. You have mechanisms which involve cross-blockchain transfers, forms of atomic swaps, pegging, and things like that allow you to move value from one to the other. But that doesn't mean they're not independent blockchains. And so then the question is, what are the consensus rules by which the blockchain is secured? So a sidechain is a blockchain, and it has some consensus rules. Maybe it runs with proof of work mining. Maybe it runs with proof of stake. Maybe it has a federated proof of authority signing mechanism. Whatever the case may be, it will have the security characteristics that these consensus mechanisms bring to it. If you took two proof of work blockchains with substantial hashing power behind them and made them sidechains of each other, they'd have different characteristics than if you connect, say, a proof of work blockchain like Bitcoin with a lot of hashing power behind it, and a sidechain that has either a very small amount of mining or a different consensus mechanism. How can we trust them? You can trust them if you understand their security model and you think that security model is strong enough. But they don't really inherit the security of the other chain. There are some exceptions to that, which have to do with merge mining, where both chains are mined together. But those exceptions don't change the rule. All right, let's keep going. Tamara asks, why have sidechains been overshadowed by other crypto projects like Ethereum for contracts and Polymath for security tokens? Well, part of the reason is we haven't seen a successful and popular implementation of sidechains, really. Sidechains are relatively recent technology. many of the underlying requirements, although sidechains were proposed 4 years ago or 5 years ago, many of the underlying technology only recently has entered into the various blockchains in order to make sidechains possible. I think probably only two have launched so far that I know of, Rootstock and just this week, Liquid. But other than that, we haven't really seen broad use, and both of those are still in beta stage. So that's why sidechains are not yet, or may never be, but they're not as popular as completely separate blockchains that have been bootstrapped with their own consensus layer and operate with their own security. Hope that answers your question, Tamara. Thank you, Gestet. Got it. Very good. Christian asks, if sidechains had to be created as a second layer from the original decentralized Bitcoin blockchain, does this mean centralization? Who runs, keeps, maintains, or is incentivized for that regarding sidechains? Great question, Christian. Sidechains aren't a second layer. The technology that connects two blockchains together is kind of a second layer. Not really. These are transactions within each of the blockchains. But sidechains are not really a layer. They're more a parallel stack, if you like. You have two stacks that operate side by side. And you're right. Who runs, keeps, maintains, and is incentivized for the security regarding a sidechain? That is the most important question. Unless you can answer that question, you can't really say anything about the security of the sidechain. And keep in mind, sidechains are not, you know, sidechain is an attribute of a relationship. To be a sidechain to another blockchain means that one blockchain has the ability to transfer value or peg value in and out of another blockchain with some form of atomic swap mechanism. Neither of these is subordinate to the other, and the term sidechain is often confusing. Bitcoin can be a sidechain to something else. In fact, if something is a sidechain to Bitcoin, then Bitcoin is a sidechain to this other thing. It simply means a chain on the side. Gabriel asks, how can assets be transferred between blockchains? How do they agree on the exchange contract if nobody owns the implementation? Great question, Gabriel. So essentially, the way assets are transferred between blockchains is through a very basic smart contract. And by that, I mean as basic that you can also implement it in a very simplified language like Bitcoin script. And these contracts are usually some form of multisig or some form of Merkle proof that allows you to essentially lock value on one blockchain and then release an equivalent amount of value on the other blockchain. And the two parties who engage in a transfer exchange between two blockchains, this kind of atomic swap between two blockchains, have to agree in order to use that technology, and they have to choose which contract to use. There can be multiple implementations that transfer value between two blockchains, between sidechains, and you choose which implementation you're going to use. And if somebody else is also using that implementation, then you can execute a swap with them. All right. Let's check in the chat room, and then we'll go over to discussing counterparty. Great follow-up question. Eric asks, is Lightning Network a sidechain or a second layer? Very good question, Eric. Lightning is not a sidechain. Lightning is a second layer. What that means is Lightning is a mechanism for for transmitting payments off-chain using an underlying blockchain for security. It allows you to route payments through payment channels, which are smart contracts using multisig and time delays. It allows you to essentially transfer, for example, Bitcoin between two participants over a payment channel without having to record it on the blockchain. And still, those two participants don't need to trust anything because the underlying Bitcoin security is the basis of trust. Now, because something like Lightning Network can also transfer, is a multi-currency routed network, you can have nodes that are participating in Lightning that are running Bitcoin. You can have nodes that are participating in Lightning that run Litecoin. Theoretically, you could have nodes that participate in the Lightning Network that run Ethereum or whatever else. The requirements for a blockchain to be Lightning compatible, to be able to interact with these routed payment channels, are that it has certain fundamental security functions, including the ability to do multisig and the ability to do time delays. And together with those two, you can implement what's called a hash time lock contract, which is the building block for payment channels and routed payment channels in Lightning Network. So Lightning Network is absolutely not a sidechain. It is a second layer. And theoretically, you could use it to connect sidechains to each other. So you can today, in fact, transmit a Lightning payment from Bitcoin, and the recipient receives it in Litecoin, which is another blockchain, because both of them are Lightning compatible. So you can effectively, that has made Litecoin and Bitcoin into sidechains of each other, with Lightning Network being the smart contract layer that connects them. All right. Yes, Lightning Network channels are smart contracts, Eric. And multisig and time delays are parts of smart contracts in some cases. I don't see why you would implement a smart contract system that didn't at least have the ability to have multiple owners or multiple signatures and time delays. So I've never seen a smart contract language that didn't have those. And even Bitcoin, which most people don't call a smart contracts platform, even Bitcoin script has the basic ability. So you don't need full smart contracts in order to do Lightning payment channels. Just the ability to do basic multisig and time delays is usually enough. Guess that in order to be Lightning compatible, each chain must execute SegWit, correct? Not really. You could do Lightning without SegWit. It's just a hell of a lot more complicated because of the transaction malleability bug. Both chains have to have a transaction malleability fix. It doesn't have to be SegWit, however. It could be a different transaction malleability fix. But it's very, very difficult to implement Lightning securely on a chain that has a transaction malleability problem, and that needs to be fixed. SegWit fixes it on Bitcoin and Litecoin. On another chain, you might have a different fix, and that would make it possible. Very good. Let's go into counterparty. Eric asks, can you explain proof of burn and how counterparty work? Could you give a particular example of how counterparty uses proof of burn and perhaps some other cases of proof of burn so I can more fully understand it? I'll try, Eric, but I'm not sure I can explain it as well as I'd like to, because I don't understand how counterparty uses it in the particulars, but I can tell you a bit about proof of burn and why that's used in different systems. Proof of burn is spending coins into an address that is provably unspendable. That means that that address is constructed in such a way that it is impossible for the address to have a corresponding private key. So when you construct an address from a public key, which in turn has been generated from a private key, those 3 steps mean that you can then spend from that address because you actually have a private key behind it. But you could just stick data into the address generator and produce an address which has a certain pattern on it. And because that pattern is very specific, the chance that you have a private key that generated that pattern are the same as if you could brute force the private key, which means 0. So practically speaking, you don't have a private key because having a private key to that address would be the same as being able to brute force from an address a private key. One example of that, you can see this in both Bitcoin and Ethereum and other blockchains, is to construct an address which starts with a very specific pattern, like 1 burn or 1 dead, DEAD, which are hexadecimal characters, followed by a whole bunch of zeros, followed by 4 characters that are just the checksum so that it's a valid address. Now, when you have a pattern like that, you take one look at it and say, that's not a vanity address. You didn't generate something with 37 characters of vanity because it's impossible to do that. You can do 1 dead, but you can't do 1 dead followed by 30 zeros and generate that deliberately as an address. Because to do that, you'd have to explore the entire key space. You'd have to brute force it. That's how vanity addresses are done. So when you see an address like that has a pattern that is impossible to recreate randomly, because it's not random, it has a very strong pattern in it, like burn or dead followed by a whole bunch of zeros, then you know that this wasn't generated by a private key. Instead, what they did was they constructed an address by putting the pattern in there and then just calculating the checksum and sticking a valid checksum on the end. That validates as an address, but it doesn't have a public key behind it, and it doesn't have a private key behind it. And so as a result, if you send money to that, no one can ever spend it because there is no private key that would produce that address. Theoretically, every address has a private key behind it. The problem is finding it. So you would have to try all possible private keys in order to find the private key that unlocks the address. So effectively, that's how you burn coins. You send them to an address that is obviously an address that could not have been generated by chance and cannot be reverse engineered, and therefore you know nobody has the private key to that address. In cryptography, we sometimes use a technique called nothing up my sleeve, which is to use certain numbers that come from that have known sources where you didn't just create that number to suit you. There's no backdoor in it. For example, let's say you generate an address which has the first 37 digits of pi. And great, you can stick a checksum on that, and that's a valid address. And anybody can check and say, oh, look, the first 37 digits, they're actually pi. So my address is, 1 if it starts for Bitcoin, 31415, etc. But if you look at an address like that, what's really nice about it is that you know that pattern didn't happen by accident. It's the digits of pi. And the chances that someone has the private key that just by sheer coincidence, when converted to base 58 and generates pi as an address is impossible, again. So that's how you build a burn address. That's how most people burn. Now, why would you use a burn address? The fundamental underlying reasoning here is that by burning coins, you generate a commitment, and that commitment is you've destroyed value in return for security. Just like when you burn energy in proof of work, that energy is gone forever, but it shows your commitment, because if you burnt that energy and you produced a block that was invalid and rejected by the rest of the network, well, you've already burned the energy, you're not getting it back, and you're not getting the reward. So proof of work has this delicate balance where you spend money in order to get a reward, but if you mess up the security, you don't get the reward, but you can't get the energy back. Proof of burn works in exactly the same way. Rather than using burning energy, you're burning coins. It's kind of like form of proof of stake, only you don't get your coins back. So you use your coins to show that you're serious about security by sacrificing them to a burn address, knowing that no one will ever get them back. One of the reasons this works is because if you have a fixed supply currency and you reduce the supply by burning some of it, what that does effectively is generate more value for the rest of the coins. So if if I had a currency that has 10 million coins and I burn 1 million of them, then all of the other coins effectively have gone up by 10% in value because 10% of the coins have disappeared. The supply has been reduced. If the demand remained the same, the value went up by 10%. And so there's that logic behind proof of burn too. Eric asks, what type of assets are being transacted in Counterparty? Is it shares of a company or a token for a project? Does it have the same functionalities of Ethereum? Yes, Eric, all of the above. You can tokenize anything. Counterparty tokens are just like Ethereum tokens. They don't work exactly the same way, but effectively they're the same thing. They can represent shares to a company. They can represent something that you can use in an application. So a utility token. They can represent attestations, so a certificate that you have a degree or a driver's license or some other thing that is issued by a central authority. In general, they can do anything a token can do. And does it have the same functionality as Ethereum? It's more the other way around. Ethereum has the same functionality as Counterparty because Counterparty was first. In fact, if you look at the history, what's really interesting is that before creating Ethereum as a separate blockchain, Vitalik Buterin tried first to implement Ethereum as a layer on top of Bitcoin using the Omni protocol, which is like Counterparty. So Bitcoin has kind of two major well-known protocols that are used for tokens, colored coins, things like that run on top of Bitcoin. One of them is Counterparty. The other one is formerly called Mastercoin and now is known as Omni. Omni and Counterparty were created 2 years plus before Ethereum, and Vitalik Buterin tried to build Ethereum first as an extension, as a more flexible version of Omni. But then he realized that that wasn't the direction of the project, and it would be better if he started from scratch on a first blockchain. You can read about that on his personal blog. It's some interesting history. So does it have the same functionality of Ethereum? Yes, because Ethereum was built with these ideas in mind and extended them to do different things from there. Back to the chat room. Uh-oh. We had some video problems. All right. Do I need to repeat any of the answers? I do have a backup video recording that I can post, but let me know if I need to repeat one of the answers because I see we had some video and connectivity problems. Okay, very good. So I will continue with the next question. Tamara asks, if one Bitcoin were colored to represent 100 million Satoshi value shares in company XYZ, how could one delink the market value of the XYZ share from the market value of the Satoshi? Really great question, Tamara. This is one of the fundamental problems, issues, or considerations that happens when you do colored coins. So if you're doing colored coins, you can only split them down to the minimum unit. So if you used one Bitcoin, you could color 100 million Satoshis and then trade individual Satoshis. Practically speaking, that's not true. In fact, because there is a dust limit of 546 Satoshis, meaning that you can't do transactions less than 546 Satoshis. So effectively, the smallest unit you can color is 500 some Satoshis. How do you delink the market value of the XYZ share from the market value of the Satoshi? You don't delink them. This only makes sense as a colored coin exercise if the value of the thing you have colored is much less than the value of the color you've put on it. Meaning that if this is a share to a company, then the share is worth a hell of a lot more than the paper you wrote it on, or the Satoshi you colored. Let me give you an example. Let's say that instead of coloring Satoshis, I'm taking US dollar bills, $1 bills, and I've got a little stamp that says this is a certificate of IBM Corporation. And I take each dollar bill and I stamp it and I sign it, and now this dollar bill is a certificate of IBM Corporation, a share certificate. It's one share of IBM. Great. Now, this makes sense if the value of one share of IBM is $30, $40, $50, $60. It makes no sense at all if the value of one share of IBM is 50 cents. Because then if I sell the dollar as a dollar, it's worth more than the share that's on it. You might say that because there's a share on it, it might be worth $1.50. But the problem is the value of the thing you've colored overshadows what you wrote on it. Or in the colloquial expression, it's not worth the paper it's printed on. And so with colored coins, you have the same problem. The thing you've colored must be worth more than the thing it's printed on. Otherwise, the economics get screwy. It's not that it stops working. It's just that now you have two considerations when you're swapping these things. You have to consider the value of the underlying asset, the dollar bill, and the value of the share certificate of IBM that's on it in order to decide what value the transaction has. And if one overshadows the other, you've got a problem. So really what you want is for the thing you're stamping to have very, very, very little value, and the thing you're putting on it, the coloring that you're doing to it, to have significant value. And we see this problem with ERC tokens in Ethereum too, which is that not so much because ERC tokens are coloring Ethereum, but because in order to transact ERC tokens, you need to pay gas, which you need to pay in Ether. And when transaction fees are high enough, the tokens that you're transacting may not be worth as much as the Ether that you're spending in order to pay the fees. So again, that's one of the problems with coloring one thing with another. Let's see what else we have. Back to the YouTube. Eduardo asks, is op return proof of burn? What's the difference between that and burning coins as you just described? Op return is proof of burn too. Op return is unspendable by the consensus rules. Before op return existed, most burns happened to specific addresses like I described before. Op return makes it easier because you can attach value to it. Mostly you don't because it's burned, but you can attach value to op return. And if you do attach value to op return, it's burned. So op return is by definition, by the consensus rules, unspendable. Marcel asks, do we need altcoins or ERC tokens for alternative uses of the blockchain? Is atomic swap the solution? Not really. Tokens and altcoins are alternative uses of the blockchain. And the real question is, can you do all of that with Bitcoin? I'm not going to even try to answer that question because no matter which way I answer it, I'm going to be demonized by each party and each side. There's a lot of people who believe that you can do all of that with Bitcoin and you don't need any of the alternative chains. And because Bitcoin can do everything and it's sound money. There's other people who believe that in fact, you need more flexibility than exists in the scripting language and consensus rules of Bitcoin. And then that these other platforms that have this more flexibility can do everything, including the things that Bitcoin does. My opinion is that this is a big ecosystem, and in this environment, there will be many different niches for different types of applications. And what makes one chain good at doing one thing, necessarily that level of specialization makes it less good at doing something else. There's always a trade-off. There's always a design compromise. If you make something very strictly interpreted, very conservative, very limited in its flexibility, that's how you make robust, sound money. And Bitcoin does that well. That means it's not very good at doing smart contracts. And the security that you got from sound money doesn't translate if you try to do smart contracts with a sidechain or other technologies around it. You can only do very limited things. That's by design, because limited things are more secure than unlimited things, because inflexible protocols are more secure than flexible protocols. So as a result, Bitcoin chooses to do things in a very conservative, inflexible way, because that generates a much more robust and secure platform for money. There are lots of other chains that have chosen to go in a different direction, and they're doing a design trade-off where they have much more flexibility. And that flexibility allows them to do the types of smart contracts that Bitcoin can't do. Or rather, it's not that it can't, it won't do, because it's been designed not to. And that flexibility comes at a cost. The more flexibility you have, the more exposure and opportunities you have for security problems, which means that doesn't mean these chains won't work, can't work, will never work. It simply means that the development process and the time to mature them and make them secure and to gradually expand the scope of what they're doing is much, much longer for those types of applications. It's going to take a lot more work to get there. But again, that may be worth the extra flexibility. And so who decides whether it's worth it or not, and what is a good fit for the application you want? Markets decide. Markets look at each one of these chains and all of these alternative uses, and they say, here's an application. Which chain is best for this application? And will gravitate towards that chain. And that means there's a wide open market for everything. I've used a couple of metaphors to explain this. Perhaps you'd like to watch some of the videos I've done on this. Probably the most relevant is called The Lion and the Shark, which describes how two systems can be absolutely at the apex of their own environmental niche, but you can't really compare them, and they can't do each other's job or compete against each other, because everything that makes them the apex for their own environmental niche makes them useless in the other environmental niche. And I think that also applies in many cases to the cryptocurrency environment. There are actual design trade-offs, and these actual design trade-offs means that you can't build a system that does everything perfectly or everything well. And in fact, trying to do that dilutes the value. If you make something that isn't specialized in doing one thing very well, then it does all things poorly. Jack of all trades, master of none. So I think it's better to acknowledge the design trade-offs, to decide what you want to focus on, and to focus so that that thing, your chain, can do well, and then let the market find which chain is appropriate for which applications. The beauty of it is that with second layer technologies, sidechain technologies, atomic swaps, Lightning Network, and all of these other things that are coming out, we can easily move value from one chain to another programmatically. And that means that all of these chains can coexist in an ecosystem where things are very liquid, where things are very fluid, where you can quickly use whichever is best for a job without hard barriers between them, at which point it doesn't really matter. Then the market can really find the best fit for each application, and we're probably going to end up with a lot of different options. Let me take one more question. This comes from Jeff. Initiatives seeking to secure people's identity and personal information using the blockchain. These will allow users to only reveal individual pieces of information to different providers. Will that solve anything, though? Won't banks still require people to provide all of the same information to open a checking account? Are there any digital ID solutions using blockchain which someone living in a village without a passport or a utility bill can use to fulfill know your customer or identity requirements? What are your thoughts on the use of blockchain for peer-to-peer energy trading, such as microgrids? Let's take the first two and address them. Digital identity is a very hot topic in the blockchain space. I am extremely skeptical that you can solve problems of digital identity simply by throwing magic blockchain at it. You see, the problem here is not the identity itself, it's the fact that centralized institutions that are regulated require identity to do things that don't really need identity to do. We're using identity as a way to control for fraud and risk in ways that don't actually control for fraud and risk. The fact that you have ID doesn't mean that you're trustworthy or that your behavior is good. And the fact that you behaved well in the past doesn't mean that you will behave well in the future. Most of the world's worst criminals were completely innocent before they committed their first crimes. And all of the historical information that we could have had on heinous criminals would show us that they were great people up until the point that they were no longer great people. People change. Bad people have ID. You don't have to be good to get ID. ID doesn't give you goodness. And the controllers and purveyors of ID, state governments, banks, etc., don't really have great insight into whether people are good or bad. So we've associated in our society this idea that if you are identified, then you are good, or if you are identified, then if you're not good, we can chase you down and impose punishments on you. Both of those have resulted in excluding several billion people from the financial system because they don't have ID, and including several hundreds of thousands of criminals into the banking system that do have ID and banking licenses, but are in fact criminals. If you create a system like that, it ends up that those who can give ID become criminals because of corruption, and eventually those who have control over other people's ID become the biggest criminals of them all. Do we need ID to transact? For thousands of years, we've transacted with cash without any form of identification. The original peer-to-peer money, cash, lasted thousands of years and didn't require any ID to transact. In fact, the idea that everybody needs to be identified before they transact is a relatively recent idea. It's a toxic idea. It's a fascist idea. And it's resulted in poverty and economic exclusion for billions of people. And it hasn't actually reduced fraud or allowed governments to stop crime and terrorism and all of the other things. It just means that the only people who can do massive crimes against millions of people are those who are funded and supported by governments. That's all it is. So blockchain ID, very, very skeptical. I don't think it's necessary for most things. I don't think it helps people. I don't think it solves crime or reduces crime in any meaningful way. And I think the side effect and the massive poverty that requiring ID creates is much, much bigger than the small benefit that you might have in fraud prevention in some areas. So massive human suffering for very, very little results. And of course, every time you have this conversation with anyone in government who's a fan of IDs, they'll tell you that if only we had more control over people, then finally, with the next law that gets passed and the next layer of controls and more power, crime will finally be eradicated. It's always just a bit more power, just a bit more ID, just a bit more control, biometrics, iris scans, etc. And if you believe that way lies fascism. Um, so no, I don't want to do blockchain ID. I want to do anonymous currency. I think transacting with peer-to-peer anonymous currency is better. And for many of the services that we have today, the world would be a better place if we recognized that it's much better to give people the freedom to transact, the freedom to interact with each other without having to use intermediaries like banks and regulated intermediaries that impose these controls and policies, which gives them enormous power for very little benefit for humanity. And on that political rant, I think we're done for MOOC 10, session 6. Bet you didn't expect that answer at the end of the course. I enjoyed it. Thank you so much for listening. I hope this has been good quality. I'm in a small hotel here, getting ready to go to a conference, so it's been a bit difficult. Thank you for your flexibility with changing the time. Unfortunately, because of a conference schedule, I had to make this one-day change. I very much appreciate all of you joining me for this Q&A session. I hope you enjoy it, and I will see you next week for one more session of the MOOC. Take care, everyone. Have a good weekend.